Imagine this. What if someone wrote a paper explaining how you could go from a 10 nanometer node to a 2 nanometer node in one step? Then companies like Intel would never have had to introduce programs like the 5YN4 or 5 years 4 nodes program to get 10 nanometers to 2 nanometers. But this is in effect what Robert Dennard did in 1974. He explained what transistor changes are needed to take a transistor with gate length of 5 microns down to 1 micron in one fell swoop. Dennard scaling, when coupled with Moore's law, meant that transistors, as they scaled to smaller sizes, kept getting faster. This scaling law has allowed the scaling of transistors to get ever faster for about 30 years, until it all ended in 2005 and we hit the infamous power wall. At this point, making transistors smaller did not make them faster anymore. But Dennard, being the genius that he is, knew this was coming. Welcome to the channel. My name is Vikram Shekhar and I write a Substack publication called Vik's Newsletter, which goes in depth into a whole lot of semiconductor stuff. I have written about Dennard scaling in quite some depth and I'll leave the link in the description below. In this video, I'll tell you the 3 laws that Dennard proposed in his original paper that allowed the transistor to scale for 30 years and the one reason Dennard scaling ended. Let's understand what the state-of-the-art transistor looked like in the 1970s. It was essentially a gate length of 5 microns on a transistor. Now, a transistor is essentially a 3-terminal device with a gate that controls the flow of charge from the source to the drain. There is an optional 4th terminal called the body or the substrate that affects the transistor's performance. Now, the distance between the source and the gate is typically referred to as the transistor gate length. Now, between the gate and the conduction channel in the silicon is an insulating layer called a gate oxide. In a 5 micron transistor, the thickness of the gate oxide was about 1000 angstroms or a tenth of a micron. And the amount of voltage that needs to be applied at the gate of this transistor was about 2 volts. And the typical voltage used at the drain of the transistor was 5 volts. The original substrate material was doped with about 500 trillion atoms for every cubic centimeter. And this was a very specific number because it was designed to prevent something called body bias. The other reason why the doping on the substrate is controlled is because it also controls the formation of what are called depletion regions around the source and drain of the transistor. There is a certain distance away from the source and drain of the transistor where there are neutral charges present. Now just look at what would happen if we simply move the source and drain regions close enough together to make them a 1 micron transistor channel. The source and drain have these depletion regions that would then just touch, and you would not have a channel through which electrons can flow from the source to drain. So this is completely a non-functional transistor. The other problem with this transistor is the amount of electric field between the source and the drain. Electric field is, in simple terms, the amount of voltage present between 2 regions, in this case the source and drain, divided by the distance between them. So if you keep the same voltage at the drain of 5 volts, and let's say the source is at 0 volts, and you reduce the distance between the source and drain by 5 times, that means the overall electric field in the channel increases by 5 times. When this happens, the silicon usually breaks down and the transistor gets destroyed. But Robert Dennard came up with 3 fundamental rules to scale this transistor in a way that it actually works. And this is what changed everything. Rule number 1, scale all transistor dimensions by the same factor k. When we reduce the length of the gate by a factor of k equal to 5, then certain other transistor dimensions need to be changed by that same factor as well. One of these dimensions is the thickness of the gate oxide, which was 1000 angstrom. That needs to be scaled down by a factor of 5 to 200 angstrom. Then the depth of the source drain implant also needs to be reduced by a factor of 5. And the overall transistor width, that is the dimension of the transistor going in and out of the screen, also needs to be reduced by a factor of 5. Rule number 2, reduce the voltage applied by a factor of K. So this means that when we applied a drain voltage of 5 volts, in the smaller transistor we need to apply a drain voltage of just 1 volt. It keeps the electric field in the channel a constant, because when the voltage scales down by a factor of 5 and the distance between the source and drain scales down by a factor of 5, the electric field is constant. A consequence of this is that the threshold voltage, or the voltage required to turn on the transistor, also reduces by a factor of K. So the threshold voltage of a 1 micron transistor would go from 2 volts to about 0.4 volts. Rule number 3, increase doping concentration of the substrate by a factor of K. When the doping concentration of the substrate is increased by a factor of K, the depletion widths, or the regions around the source and drain where it is charge neutral, also decreases in width by a factor of K. This is very important to keep the source and drain regions in the transistor from touching each other when the transistor is scaled down. Now, all this means that the current flowing through the transistor from the source to the drain also drops by a factor of K. When they tested this theory proposed by Dennard and manufactured a transistor according to these rules, they found that it worked perfectly. So well, in fact, that it surprised Dennard himself, who wrote in his original 1974 paper, the exact match on the current scale is thought to be fortuitous, since there is experimental uncertainty. But there is one transistor parameter that did not scale, and one that we haven't spoken about yet. In fact, Dennard pointed this out in his original paper, with enough foresight to know when his own scaling rules will come to an end. He writes, in order to design devices for operation at room temperature and above, one must accept the fact that subthreshold behavior does not scale as desired. So subthreshold behavior is a very important property of a transistor that determines how quickly a transistor turns off when the voltage on the gate is put to a very low value. When a transistor is completely off, it shouldn't be leaking any current at all. If it does, it's not really off, is it? Now, as transistors scaled to a gate length of 90 nanometers, or roughly 1/10 the size of the transistor that Dennard originally proposed in 1974, Dennard's scaling laws ended because transistors would leak so much current even when they were off that the chip would heat up, and any benefits obtained in terms of transistor speed were no longer useful. When coupled with Moore's law, which states that the number of transistors in a chip will double every 2 years, Dennard scaling implies that the increase in transistor count comes with no thermal penalties. And the benefit of making transistors smaller is that they were faster, because the amount of time taken for an electron to go from the source to drain is much lesser if they're closer together. After the end of Dennard scaling, the trajectory of compute has taken an entirely different path. We now treat entire data centers as units of compute and not just a single chip or a transistor. Even though we don't really rely on Dennard scaling anymore, it remains an important piece of history in the field of semiconductors and has enabled the world as we know it. Thank you for watching.